The modulus and the exponent values are chosen during the key setup. RSA key setup is done once when a user establishes their key pair, and the key replacement or reestablishment is done very rarely. A user generating the RSA key selects two large prime numbers p and q and compute the product for the modulus n. Because p and q are primes and n is equal to p times q, there are p minus 1 times q minus 1 numbers between 1 and n that are relatively prime to n. In other words, the greatest common divisor of n and the number is equal to 1. We will use phi of n to denote the number of integers between 1 and n, which are co-prime to n. Phi of n is called Euler-Totient function in number theory and plays a big role in the rest of the key setup for RSA. After establishing p, q, and n, the user selects either the public key E or the private key D to derive the other. Let's suppose the user selects the public key E. The public key E is selected randomly with the constraints that E is smaller than phi of n and is relatively prime to phi of n. E is also usually a fairly small integer to make the RSA encryption process more efficient. Given the public key E, the user derives the private key D by solving E times D is congruent to 1 mod phi of n. In other words, since 1 is the multiplicative identity, we find D that is a multiplicative inverse mod phi of n. There's an algorithm that does this, called extended Euclidean algorithm. Extended Euclidean algorithm can be used for finding the multiplicative inverse mod phi of n by plugging in E and phi of n as the two inputs of Euclidean algorithm and using the fact that the greatest common divisor of E and phi of n is equal to 1 by the definition of E and how it is selected. It is critical that the two factors p and q, are kept secret, since if they become known, the system can be broken. Also, different users with different p and q will have different moduli n.